Good afternoon, dear colleagues. It's my great pleasure to be today here and to present our results on fatigue aggro modeling in welded stiffened panels considering residual stresses. So this is me and this is my colleague from Germany, Professor Schmauder. We had a common project and we produced this work and I will present it here today. Also, I wish to thank you to my former students. I mentioned just 3 here, but many more of them were involving too many steps that really became what we have now. Because it's an iterative process and it needs validation and evaluation. Now we have something that I think it's worth to present. So at first, I will give a brief introduction, then presented fatigue test results, and then we describe Hamilton element analysis and modeling of welding residual stresses by using ANSYS program. Then I will present some long crack propagation models, and then we will apply some of them to our example, our experiment, and we will compare experimental and simulation results. We'll draw some conclusions and give some ideas for future work. Before we start, I just put here this systematization of total fatigue life, which was given by Chive in his book. And we have initiation period, then long crack growth, and final failure. And what we are doing here, we will consider this part, the cracks are already long, and we'll take into account residual stresses. Without residual stresses, it's fine, quite straightforward, but residual stresses may significantly influence fatigue crack growth rate and propagation. So, when we don't have residual stresses, this is a typical crack growth behavior. At first we have slow and a small crack growth rates, and then crack propagation speeds up. So when we consider a simple plate or without residual stresses, we have this situation here, but residual stresses may change this. And with our model, we are here in the Paris region, and we will apply some power law models like Elbert and Chive. So this is the problem which we have when we speak about stiffened panels and fatigue. We have seen already this picture several times here, also at some plenaries. And this is so-called multiple site crack problem. And it's not really only to be found in airplanes, but also in ship structures, where we also have stiffened panels, and this is typical deck structure of a ship. What do we have here? This is what you see here. The deck turned upside down, so you have your plate and longitudinals and bulkheads, and then you have complex geometry here, where welds are meeting each other, so stress concentration sites. So here crack can initiate and the cracks propagate through the longitudinal and enter the deck plate. And this is when you have this at several locations, then these cracks may join, and this is what you have as a result. This is a 20-meter crack long in the Castor tanker ship. Luckily, this ship managed to come back safely. It has not encountered any big waves or storms. Otherwise, it would, like many others, be lost. So this problem is basically a multi-scale problem, and in total fatigue life, as Chive mentioned, all stages should be considered. But what we present today is propagation of long cracks, so it's this part here, and we consider the effect of residual stresses. And to mimic what we have in a deck structure, in the deck structure of a ship, this situation here, we designed a specimen which looks like this. It's a plate with welded stiffeners, and here we have cut stiffener and a crack which is already in the plate, and it looks like this. So we consider basically two situations when we have a single crack damage and three cracks at each stiffener. So today we speak more about this, but we will show you experimental results for both cases. Simple specimen with a single crack SP1 was considered, and with three cracks. And the material and the consideration is mild steel for welding with yield strength 235 megapascals, and this data, as you see here, it's a typical material for welded ship structures. And the specimen looks like this, with cross-sectional area, and it was loaded with delta sigma related to intact area 80 megapascals, and for that was needed almost equivalent 10-ton cyclic loading. And this is R ratio, which is basically close to zero, just a little bit above to avoid shocking in the experiment. And for specimen with one crack, welded specimen, this is the fatigue life, and for the three cracks it's much shorter, several times shorter. And what we can see here, it's not what I showed you before. It was like that something, and now it's propagating probably at the same crack growth rate. And this is what we wanted to investigate and to see what was the reason for this. And for that we use a power law. A typical power law is Paris equation. So as you know, in logarithmic scale, in a crack growth rate diagram, d over dn with respect to delta k, we have a straight line, and with some simple mathematics, we come to Paris equation. To this equation is the equation which this old man, who is walking around here, produced like 50 years ago. And then we can calculate number of cycles from this equation in this way here, that we integrate Paris equation. And we started with Paris equation, but today we have like 8 different power law models and even more. So I just mentioned some of them because we use another two which you will see later. And I want to mention that we integrate the fatigue crack growth live by using numerical simulation procedure developed in MATLAB, and we have piecewise distribution between discrete points, and then we also integrate this numerically to get fatigue number of cycles. And we are now back to our specimen. So we consider this one with a single crack, with a central crack, and this is intact. This is intact, and here is crack. The cracks look like this. And in 500,000 cycles it was broken. And what we want to see, the influence of residual stresses on fatigue crack growth rate. If we have a welded plate, this is a typical residual stress distribution in longitudinal direction, where we here reach or may even exceed yield strength, and this area here makes equilibrium to this area, where here we have tensile stresses and here are compressive residual stresses. And the well-known function is so-called green function, and it's a analytical expression for this. These two areas below and above are equal, and we can introduce residual stresses into our finite element model by using ANSYS and any-state command. So, and for that is a certain fine mesh needed, and with 1 millimeter, with 1 millimeter element size, we could do this successfully. And this is what other authors measured who are concerned with crack propagation and residual stresses in deck structure of a ship. So they measured residual stresses and they obtained, you see, this was measured, and they tried to idealize this with such rectangular distribution. So, and you have stresses which reach tensile yield strength here at this part. So this is, for example, 1/4 is under tension and 3/4 is under compression. And so we assume that in our model this residual stress distribution, because it should be idealized, it's more or less random, but it's always like this. And I want to point out that real distribution is between rectangular here and triangular. So that's. So we introduce residual stress into our stiffened panel and calculate the stress density factors without residual stresses and with residual stresses. So at first we consider rectangular, and residual stress are introduced here. And then we calculate stress density factor. This is without residual stresses, and this is with or including residual stress. You see that at short crack length, initial crack length was 2.8 millimeters, but it's much higher due to residual stress, and here is lower. And then we used we use these K values to calculate, to simulate fatigue life. And we used Elber model, which you know very well from the literature. And in the Elber model, so we need R ratio. That's local R ratio, which depends on K maximum and K minimum. So this is this, and U function depends on this R ratio. And then we have effective stress density factors, and as explained before, by integrating power equation and this delta K effective, we can simulate fatigue life. So without considering residual stresses, we have this, what we have seen before. And with considering residual stresses, simulation fits quite well to experiment, maybe even too much, too well, to good agreement. So that we consider some other distributions and other models to see what happened then. So two extreme cases are rectangular and triangular. And then we calculated the case again for rectangular and triangular. We need R effective for both cases. And then we need U functions, that's for Elber model and for Shiva model, and we plot them here. And finally we get K effective for rectangular and triangular Elber model and Shiva model. And we again compared simulated life with experiment. So basically all these models give quite good agreement with the experiment, much better than without considering residual stresses, which would be something like this, what we have seen before. So then I come with this to conclusion. It is very important to consider residual stresses in fatigue crack growth simulation in welded stiffened panels and other welded structures as well. Maybe we can also consider secondary bending in the future and consider some more power loads for this. And that would be all for me. I would just want to acknowledge two projects which supported this investigation, and thank you all for your attention.
Okay, thank you.